Hi, my name is Samuel. I'm from the University of Southampton. I'll be talking about energy-aware modeling of batteryless wireless sensor nodes. Here's an overview of my talk. First, I'll describe how batteryless systems are different from conventional embedded devices, thus making the case for the need of a virtual prototyping framework tailored for batteryless. Next, I'll present the tool's requirements and the desired features so that the tool can effectively model batteryless device. I'll then introduce our work in extending Fused to enable the virtual prototyping of a full energy harvesting wireless sensor node. Finally, I'll give a demonstration which will highlight some key aspects of the extended Fused. The process of designing an embedded system may look something like this. First, there is the research or pre-design stage, where we survey the available hardware and software solutions according to the specifications of the application requirement. The output from this stage feeds into the design repository, and a candidate solution is designed and tested. This stage may involve modeling using the simulator and may involve multiple iterations. Once we are confident that our solution meets the product requirements, we can build a hardware prototype and do more tests and then move on to production. For energy harvesting devices, it would be beneficial if the power characteristics of the subsystems are made explicit early in the design process, and this is especially true for batteryless systems. Let's take a closer look. Like any other complex designs, wireless sensor nodes benefit from abstractions. For example, the design of the power subsystem and the functional subsystem can be reasonably decoupled after the design teams agree on some interface. However, this does not apply to energy harvesting batteryless devices because there is innate coupling between the functional subsystems with the power supply. Due to the lack of sufficient buffering, the system is exposed to temporal variations in the energy harvesting source. Some of the implications include unpredictable brownouts of the microcontroller and the variable voltage rail affecting sensing accuracy. Mm, we'll talk a bit about simulators. Conventional simulators, like Gen 5, of computing systems, assume a stable and always available power supply. They are hence unsuitable for modeling battery systems. We would like to propose a custom tool. Here are some of the features that we would like to have in our custom tool. Our custom tool should be a virtual prototyping framework that models the full energy harvesting device in a closed loop. What I mean by a closed loop is, for example, a piece of executing code would have an associated current draw profile. This current draw profile would set the operating point of the power delivery circuitry. This in turn affects the supply rail characteristics and could, for example, if the current draw is more than what could be sustained by the power supply, a drop in the supply rail voltage will ensue. This in turn affects code execution and could potentially result in device failure or incorrect functionality. Another feature that we would like in our virtual prototyping framework is coverage. So it should cover all the significant components in a wireless sensor node. That means the sensor, the microcontroller, the radio, and all the other circuitry in the peripheral. We'd also desire sufficient fidelity. So this means that we want enough time resolutions to capture all the events that happen on the microcontroller. I'll give you an example. In intermittent computing, it's quite common to have a software solution to handle the power failure event. And in order to accurately simulate that, we would like the system to be able to simulate at least at the frequency of the microcontroller clock, so a few megahertz perhaps. And next, we will also want, because we are simulating energy harvesting wireless sensor nodes, we would like to have models of the physical stimuli This could be weather, temperature that feeds into the harvesters and these sensors. Finally, for a useful virtual prototype, we would like the prototype to be modular and extensible, and it will also benefit from fast simulations. This brings us to Fused, which was first introduced in its past this year to simulate intermittent computing. Now, Fused stands for Full System Simulation of Energy-Driven Computing. Fused can simulate the execution of compiled binaries at the cycle level and includes a power model that is readily adaptable to this work. Since then, we have extended Fused such that it can now simulate an entire wireless sensor node class device. Shades of gray in this diagram indicates extensions in this work. We added models for on-chip peripherals, such as SPI for on-chip onboard communication, and external peripherals and circuitry, like the power management circuitry and the harvesters, as well as sensors and radio modules. We also include in the code repository drivers and software stacks, which we'll talk more about later during the demo. At the time of writing this paper, the radio channel emulator shown here um, simply dumps the physical layer packets onto the console, or standard output. It includes the payload and metadata about the packet. The modules in Fused are written in System C and C++, and we take advantage of the analog mixed signal extensions to System C in this work for the power delivery circuitry. A word about a power model. So in Fused, active components such as the microcontroller, and the radio module and sensors would log events and states. Now, these events and states are used by the power estimator, the current estimator, to generate a current load on the power delivery circuitry. This sets the operating points of various electrical components along the power delivery path, and this, for example, would determine the efficiency of the power converters. Here is an example of a subsystem that is modeled and fused. So this is a radio module from Nordic Semiconductors. The key components in this module are the communication interface, in this case SPI, and the RF interface to the channel emulator, responsible for dumping the physical packets, and the state machine. There are also other device-specific data structures in the subsystem, such as FIFOs for data. And then on the right, you can see a representation of the state diagram. So the state diagram, the state machine diagram, captures the transient states and the states, and it is annotated with the current draw of each state. And these current draws are used in the power model. Now let's look at an example full system. So here is an example of a full virtual prototype of an entire system that's captured and fused. This is a solar-powered ambient sensor node, which includes the NRF radio module, a BME280 ambient sensor, and an MSP microcontroller, among other stuff. On the power delivery path, there are monitors and power converters and the solar cell. We can simulate such a system in Fused and get traces like one shown here. In this case, we have a simple piece of C code that is loaded onto the memory model of the virtual prototype and executed for 14 milliseconds. We flash the same binary onto a physical, like a real MSP480 launchpad, and the launchpad is connected to a BME280 sensor and a Nordic radio on the breadboard. We also include a shunt resistor to measure the current draw and with some amplifications. And then the two traces are shown here. So the measured trace is the blue one, and then the orange trace is the current generated produced from the virtual prototype. Now, they correspond. So, for example, during a sensing event, you could see the the increase in current for the temperature measurement, and then the pressure measurement, and the fall after. And what's most obvious is here during a TX event. In the demo, we will be adding a receive window behind this TX event. Before we do that, let's note that we also plot the voltage across the input capacitor, and that falls, and the rate increases as the current increase, which is especially steep here during the TX event. In this quick demo, I will go through the project directory structure and introduce the various components of Fused. I will then run a simulation in Fused and view the output traces in GTK Wave. The simulation is the exact simulation used to obtain the traces shown in the slides. I will then use GDB to step through the target code and demonstrate current and voltage profile generation, which is in lockstep with code execution. Finally, I will add a few lines of target code to open a radio receive window immediately after the radio transmission. I will be running Fused in Ubuntu on the Windows subsystem for Linux. Here's the project directory structure. The README contains information about getting started, including build instructions and how to run Fused. The MCU directory contains the models for microcontrollers, including the CPU cores and on-chip peripherals. The SD directory, which stands for serial devices, contains sensors and radio modules. The PS directory, which stands for power supply, contains the power and power delivery path models. The boards directory contains the top-level hierarchy module, and this is where the various components are hooked up. Finally, the software directory contains target software, which are to be loaded onto the virtual prototype. After building Fused as per the README, the Fused executables can be found in the build directory. This launches Fused, and Fused will be listening on port 51000 for a GDB connection. Next, we will use the GDB client to connect to this socket and load our binaries. We'll be using the 2-chain from Texas Instruments for the MSP 430. And here is our example software. Now we have loaded our binaries into the virtual prototype. Let's then execute this program to completion and view the outputs in GTK Wave. We'll be interested in VCAP, the voltage across the capacitor, and ICC, which is the current consumed by the system. First, we need to set them as analog signals. then zoom out, and you could already see the trend, but let's insert some height extensions so that we can see more clearly. Okay, and that's two output traces, or not traces, from fused. Notice that there's a bunch of signals that are included here, and because this is a virtual prototype, all signals, including internal ones and registers and variables, can be traced. We'll be repeating these tasks, this time with breakpoints to show current and voltage traces in lockstep with code execution. We will be using the text-based graphical interface. Now we have executed up to the first line of code in main, and if we look at GTK wave, it has captured that first bit of execution. So this is the boot current trace. Let's set another breakpoint at right before the radio to capture the trace for the sensor operation. So break at 100. Now in GTK wave, we should have captured that. Yep. So this is the point where the sensor starts operating, and it's now let's execute the rest of the code. Note that we have dumped the radio packet and metadata about that packet on the console. Next, let's add a receive window right after this transmit event. So I have the code here. I'll just uncomment them. So this is in the main file of the target software source. And then we need to compile this. So split plane terminal bash terminal bash cd software build. Right, that's compiled, and it should be automatically loaded here. Let's see. Launch the virtual prototype and okay, load, and let's remove breakpoints. Let's execute the completion. Now if we look back at GTK Wave, we should see our receive window. Yep, and there it is. Alright, and that concludes the demo.